which is kind of small. And this is really just so that I could make a figure where I can visualize that. In practice, when we are training a model like GPT-2, it's usually something around 1024. So you have like 1,000 tokens in one row instead of just 4. It's really just so that it's easier to visualize, right? Yeah, okay. And so this is how the input data would look like. So we have mini batches similar to deep learning, where in this case we have 1, 2, 3, 4, 5, 6, 7, 8, a batch size of 8, and each training example consists of multiple tokens. And then the targets are really the same as the inputs, except shifted by one position. And yeah, so this is in a nutshell how we prepare a data set for an LLM, and we will later train our LLM on this data set. And just like as a warm-up optional exercise, maybe pause this video at this point and prepare your own data set. So if you have some favorite texts, maybe something you have written, or maybe some other public domain book you like, please feel free to download it and put it into the folder where you have this notebook, and then just run this code instead of the verdict here at the top. Run this code on your own favorite text, and then you can actually also use this text in the later sections, basically. So it's just like a small, maybe fun optional thing to do. Okay, so now after we covered the input part, how we tokenize texts, let's go to the next part, the LLM architecture. So here in this notebook, I want to talk about a bit of how an LLM is structured, but this is only on a big picture level. So there will be a lot of individual components, and this is a 3 to 4 hour workshop and not like a 30 to 40 hour workshop. So in this case, we will be focusing on the big pictures here. So here in this notebook, we will be talking about coding LLM architecture, but the top-down view. If you're interested in further details, you can check out my GitHub repository here corresponding to my book, where I have more notes and on every, let's say, individual component that we code. But for this video, let's focus on the bigger picture. So suppose we have a LLM like shown here. Previously, we talked about taking input text and then tokenizing this input text into these individual token IDs, and inside the LLM they get then processed by so-called embedding layers that produce continuous valued vectors, and those go into so-called transformer blocks, and then there is an output layer, some post-processing steps, and then we get text back. So the goal again is to generate one word at a time with the LLM, and that's how LLMs are also pre-trained. So when you use something like ChatGPT, of course it's more sophisticated, so you will notice it can follow instructions, but typically when we start developing an LLM and pre-train it, it will require you to provide something like a starting text, a starting context. For example, like this, every effort moves you. And then based on the starting context, it will provide basically the next word, in this case, forward. There are a few more nuances to that, how this next word is generated. And we will get to that by the end of this notebook. So here it's more like the big picture. We have the LLM, and inside there's something called a transformer block that gets repeated a number of times. And that produces basically the output text. And this is the same for all kinds of architectures. It's GPT, Google's Gamma or Gemma. Microsoft's Phi, Mistral, Meta AI's Llama, and so forth. So they all
So we have tokenized text, all of the tokenized, and an embedding layer on top of it. Okay, you have an embedding layer on top of it, and a transformer block, and an output layer. Transformer block, I think, is the model. I don't know. Let's see. Building an LLM, data preparation, attention mechanism, LLM architecture. Okay, we are in this block now. Attention mechanism is when we tokenize all of it, I think. And we have pre-training, training loop, model evaluation. pre-training. Training loop is called weight loading. Okay. Model evaluation is fine tuning. And load pre-trained weights and fine tuning. What the fuck? Okay, we contrast some stuff. Classifier data with, we either fine tune it to be a classifier or a personal assistant. Okay, whatever that means.
Kind of rely on the same underlying concept. And here's the architecture in a little bit more detail. And I know there is a lot of technical jargon on this one, which we won't go over here. But if you are familiar with deep learning, some of these things might be familiar to you. For example, dropout or layer norm, or these are residual connections. There's an output layer, feed forward, which is basically a multi-layer perceptron, and this consists of linear layers with non-linear activations and so forth. So again,
LLM. No, I didn't mean that, bro. Full screen. Full screen. Yeah. So let's go here and what is it? LLM. LLM. Prompt engineering for LLM. What the fuck is prompt engineering? What the fuck's prompt engineering, bro? Model context prompt. I don't know. Prompt engineering. What the fuck is that? Uh, hands-on LLM service and what the fuck? LLM practical. Okay. Okay. You a sucking dick for a foreign car. No, no, no. Mia Khalifa, Mia Khalifa, Mia Khalifa. Boy, hit or miss. Best they never miss, huh? You got a boyfriend, but he doesn't kiss ya. Yeah. Mia Khalifa, Mia Khalifa, Mia Khalifa. No. Mia Khalifa, Mia Khalifa, Mia Khalifa, Mia Khalifa. Boy, hit or miss. I best they never miss, huh? You gotta advance framework.
This workshop is not the workshop to go into these details. I wish I could, but due to time reasons, I have to only give you the big picture overview. And the takeaway here is, I would say, that different LLMs are very similar to each other. Even though they might be large and much larger than others, they are still underlying the same concepts. So here on the left-hand side, GPT small is a 124 million parameter LLM. Of course, the L in LLM stands for large, so it's small large language model. But there also is this variant called GPT-2 large, which is 1.5 billion approximately. And so this is about more than 10 times larger. But the only difference really is that this number of times the transformer block is repeated is now 36 instead of 12. And we have 20 heads instead of 12 heads in this masked multi-head attention module. So if you are familiar with convolutional networks, in convolutional networks there is something called channels, and the heads is essentially analogous to those channels. And there's also a detail where they use rotary embeddings. Sorry, not here. That's actually Llama. So here we use absolute embeddings, and they have a different embedding size. So when we have the token IDs, we go from token IDs to continuous valued vectors. And in this case, each token ID is represented by a 768 dimensional vector. In the large model, we have 1280 dimensions. So it's just making the embedding size larger. So each vector representing one token is essentially larger.
Natural language processing. With Spark NLP.
So here I have for comparison also a
Small language models. Fuck you.
different architecture. Llama 2, but even that one is very, very similar to GPT. So here in this case, what they've done is they swapped layer norm with RMS norm, and they removed dropout. So dropout is not very popular anymore in large language models, so most architectures don't use it anymore. And yeah, other than that, yeah, they use the rotary embeddings, positional embeddings. So it's just a different form of embedding the words. It's just like a cosine, sine kind of wave form to rotate the embeddings to create some notion of position. But again, this would be a great topic for a different video, maybe hopefully in the future. Another detail is they swap the activation functions. So instead of Gelu, they use Silu or Silu. So they're just, honestly, I would say minor implementation details, but fundamentally they use the same architecture really. So suppose we are interested now in working with this 124 million model. Here is just some, hyperparameter configuration to get this architecture I'm showing you here. So we don't need to really go over those, but n layers is the number of times the transformer blocks get repeated. I could also have called that n transformer blocks maybe. The number of heads here, embedding dimensions. So here, this would be corresponding to these, right? And the context length is how many tokens you can provide as input. So newer LLMs, they support, let's say, up to 4,000, 8,000, sometimes even more tokens, but it makes it also more memory intensive. So 1024 is actually, yeah, quite a good number for experimentation. And the vocabulary size, how many unique words are in the vocabulary. And this corresponds in our case to the BPE tokenizer, which we implemented in the, or not implemented, but loaded in the previous notebook. So when we loaded that somewhere here, we used the BPE tokenizer, which can represent 50,257 words or tokens. Yeah, we disable dropout. It's not really needed. So honestly, it just makes the architecture more complicated, but we can also enable it, so it doesn't really matter. And QKV bias, it's implementation detail I did here because maybe I shouldn't discuss it. It's too much detail here, but the masked multi-head attention layer uses linear layers. And it's usually common to have a bias unit for the linear layers, but modern architectures don't use that anymore. So in modern architectures, the linear layer is essentially just a simple matrix multiplication, especially when it comes to the QKV matrices in an architecture. So it's basically, instead of applying this affine transformation, we have a linear transformation, a linear matrix multiplication. However, the original researchers who implemented GPT, so the original GPT model, they did use a bias unit for the QKV matrices, which is a bit weird, but it's maybe just what they did. But then if we want to load these weights later, we have to match that. So in this case, I have a toggle, so I can, I can add these, so we can later, we can later load the pre-trained weights. Now, this is just a big picture overview, of course, but there's one more thing I wanted to talk about, and that is how the input-output looks like. So if we have the input text here, it gets tokenized, as we've talked about in the previous notebook, and then it goes through the embedding layers. We have the transformer blocks and so forth, the file layer norm, and then an output layer. And the output actually, unless we do some post-processing, the output of this output layer, because it's just like a matrix multiplication, a linear layer, how it looks like is we get a big tensor here. So we have 4 words, 1, 2, 3, 4 tokens in this case. So we have 4 rows, 1, 2, 3, 4. But each of the columns here, so we have actually 50,257 columns. And the columns here, they correspond to the vocabulary. So it's a bit abstract here. I couldn't, of course, show all the 50,000 dimensions, but we are this whole thing in the whole row is the second position would correspond to token ID 1. So if I go back a bit, the previous notebook, we had the vocabulary at some point here. So first token ID would correspond to the first entry, the second token ID to the second entry, and so forth. And in the same way, each column corresponds to the token ID. So the first token ID, second, and then the last token ID in the 50,257 dimensional vocabulary. So this is really how you would implement the LLM. And I'm not showing you the implementation details because this would be a 10-hour lecture, but I have them here in the supplementary file. And if you want to, it's also described in my book and in the GitHub repository corresponding to my book. So if you want to find more information, I have more notes there. So here we are more focused on the big picture. So let's actually create some simple data sets. So I have just initialized the GPT model. And here I'm getting my BPE tokenizer that we talked about in the previous notebook. And I have some two text inputs. Every effort moves you and every day holds A. And I want my LM to complete these texts, essentially. So I'm creating a mini batch. So I'm not using the data loader from the previous section, just to keep it simple. I have a very simple input. So the first training example are these 4 tokens, and the second training example are those 4 tokens. So this corresponds to text 1, and this corresponds to text 2 here. And let's put this into the LLM and see what the results are. So you can see the output shape is now 2 times 4 times 50,257. So this is a shape and this is a corresponding tensor. So what do these numbers mean? So we have 2 input examples, right? So we have 1